Thank you very much. It's great to be here. And this title, Why Do You Look Up at the Heavens? Actually, excuse me, water. I need some, yes. It's from Scripture. It's what the angels are saying to the apostles immediately after the ascension. Yeah. So easy a child could open it. Are there any children here? It's also, incidentally, that why Men of Galilee, why do you look up into the heavens, was also the theme of the first homily preached against Galileo by the Dominicans in Florence. Later on, the Dominicans became Galileo's friends and the Jesuits were his enemies, so he was equal opportunity. It's in two different, a little bit louder. It's in two different senses that I want to ask that question. Why are we as a society interested in doing astronomy? And why do we as individuals choose to do that kind of work? So let me tell you a little bit about the work and the kind of work I do. My field is the study of meteorites. Meteorites are the rocks that fall out of the sky. They're samples of the asteroid belt. Sometimes they come from the moon or Mars. And with luck, they actually might be collected. They might be stored in museums. Curators will then take care of them. They're, of course, very rare and very valuable. And one of the things, if you've ever known a librarian who thought their job was to protect the books from readers, curators are there to make sure that nobody touches the rocks, especially not scientists. When I arrived at the Vatican Observatory more than 30 years ago, I discovered that they had one of the world's larger collections of meteorites, and they did not have a curator, so I named myself the curator and gave myself permission to start these experiments. The collection actually came to us from the Marquis de Mauroy. My French is not good, but I know there's a hockey player whose name is spelled L-R-O-Y that you say wa, so I think I'm getting that right. And he was a French gentleman scientist of the old school. He collected meteorites and minerals by purchasing them from other people who gathered them. And he had, by the end of the 19th century, one of the largest collections in Europe. At that time, the Vatican was working to be established as an independent nation with all of the trappings of nationhood, one of those trappings being a national museum of natural history. So he proposed to donate parts of his collection to start that museum. The Vatican looked around and said, we don't have room for it. So they got a handful of pieces, and that was about it. By 1929, and the area out in Castel Gandolfo was given back to the Vatican, suddenly we had the Papal Palace. His widow donated the rest of the collection. What do I do with these meteorites? One of the principles that I'm interested in is measuring the physical properties, because this is a collector's collection. It's a little bit of everything, not a whole lot of one thing. I don't want to make measurements that are going to destroy the meteorites, but something where I can do the same measurement on all the different types and do a survey to see how the density changes with type of meteorite. I could go in long times of all the different types. One of the numbers that's useful in trying to understand meteorites and how they're put together is something called heat capacity, which is the capacity to hold heat. In other words, how much heat does it take to raise the temperature by 1 degree? How much heat is given off when you drop the temperature by 1 degree? And these are numbers that modelers used that I was looking for that no one had ever measured. So I got this collection. I'm thinking, how do I measure that? The right way to do it is if you have a big $1 million machine at a university. This machine is run by a fellow, the guy in the picture, whose name is Sayo Peel, who is actually a Jesuit priest. This is at Boston College. And you see the tiny little bit of rock. It's a couple of millimeters across. You carve it up, you glue to something to either side, and then you can measure, well, It takes a day to make the measurements really precisely, and then another day to do the standard. So it's 2 days for every measurement, plus every measurement you've got to carve up the meteorites. And yeah, I'm my own curator, but I don't want to have to carve up every meteorite in the collection. So we have a few representative ones we've measured this way, but the others, we came up with this great idea. You start with liquid nitrogen. It's basically 70 degrees Kelvin, just above absolute zero. You drop the rock in the liquid nitrogen. The rock is at room temperature. So it starts boiling away the liquid nitrogen until the rock is at liquid nitrogen temperature. Well, notice what happens on the graph. You start with the blue or the black line. When you do nothing, the nitrogen is slowly boiling away. Then you drop in the rock, and the weight of the whole system jumps up by the weight of the rock. But then it starts boiling away nitrogen. So all of that is the nitrogen that's boiled away due to the heat in the meteorite. That's the amount of heat that came out of the meteorite to lower it from room temperature to liquid nitrogen temperature. You figure out how many grams of liquid nitrogen are boiled off per joule or calorie of heat, and then you have a way of measuring the heat capacity. So, I'm a theorist originally. Where do you get a doer like that? I went and bought a thermos bottle at Target. Where do you get the liquid nitrogen? We are located in Castel Gandolfo in the Pope's farms, where the Pope for many years had their own milk made in the Pope farms by papal cows. If any of you are familiar with animal husbandry, you realize to get milk from a papal cow, you have to have a papal bull. Well, no, sorry for the joke. Actually, nowadays, you don't do that. You keep bull semen frozen in liquid nitrogen. And then when the cows get pregnant, then they start giving off milk, et cetera, et cetera. Which means that right next to us is a farm with a huge tank of liquid nitrogen. And anytime we need it, we just go over with a bucket and say, can we have a little bit? Pretty slick. Well, actually, in real science, it's never that easy. So this is my big, fancy, not $1,000,000 apparatus. I've got a scale connected to the computer, which records the weight every 3 seconds. I've got the thermos bottle. It's sitting on a box. Why is it sitting on the box in the scale? Because otherwise the scale would get cold, and that would change the qualities of the scale. I've got a container on top. Why is that little container there? Because if you leave the nitrogen out to the air, then water vapor on the air will freeze on top of the liquid nitrogen, and that will change the weight, which is what I'm using to measure the amount of heat coming off. So where did I get that marvelous little container? At a €1 store. This is designed to hold spaghetti. One of the joys of doing work in Italy. But after a couple of years of running through all of those samples, we started getting data. And then somebody came to me and said, wait a minute, you drop things in liquid nitrogen that makes them fragile. In fact, if I had an iron meteorite and I want to break it into smaller pieces, the technique is to drop it in liquid nitrogen. Don't your meteorites shatter? So I looked up the paper. This is why you have a library with literature. You can break up an iron meteorite by dropping it in liquid nitrogen and then hitting it with a sledgehammer. So as long as we don't hit these with a sledgehammer, we're in good shape. Details like that are the things they never tell you about in science class. So, my buddy Bob Mackey and I have been making measurements like this for about 10 years. We've got hundreds of meteorites for which we have an average heat capacity, and then a few for which we have a very detailed heat capacity as a function of temperature. It's a nice data set. And the question is, why? Why are we doing these experiments? It does turn out that asteroids will slightly shift their orbits because they get heated on the sunlit side, and if they are spinning, then that heated side is turned to one side and it re-radiates more energetic infrared photons in that direction, which will then change the energy of the orbit. Which direction depends on which way it's spinning. How much effect you get depends on how long the heat is retained in the surface of the material, which depends, among other things, on the heat capacity of the material. So our ability to predict how an asteroid might be jolted out of its orbit until it hits a resonance and eventually comes and hits the Earth, if you're going to model that, you need our numbers. But that's not why we're doing it. I mean, it's Thursday morning, and I'd rather sleep in, and this can be, rather tedious work after a while. I'm not getting up in the morning saying, I've got to hurry up and make these measurements, or else in 45 years, Earth is going to be destroyed by an asteroid. Number one, I don't believe that. And number two, that's not what is getting me up this morning. What's getting me up this morning? So why do we do it? And why does anybody pay for it? Two parts to the question. Why does society support it? Why am I doing it? To do big science costs money. The way it's done now in America, of course, financing of science is crazy right now, but typically, the astronomers get together, they create a number of white papers, they come up with a thick book that they hand to NASA saying, these are our priorities. 20 years ago, it wasn't that easy. 20 years ago, we got money to send a spacecraft to Pluto. There is Pluto. New Horizons was the name of the spacecraft that went there. Why did somebody decide to go to Pluto with New Horizons? Because the people who had proposed the mission were at Johns Hopkins University in Baltimore, and the senator in charge of the finance committee that had to make the decision happened to be from Baltimore, Maryland. This is called earmarking. This is considered generally a bad thing. Well, the New Horizons mission flew, and it was successful, and got these cool little pictures of Pluto with the heart on them. But because it got the money, other missions did not get the money. The mission that didn't get the money was a mission to Europa, which almost certainly has oceans, salty oceans, under the ice crust, with a really good possibility of life forms in those oceans. You heard that I did a master's thesis at MIT in 1975. It was exactly on that topic. We're finally sending missions there. The Europeans and the Americans have 2 missions going to Europa. By the time they deliver their data, I'll be 80 years old. So that's what I missed out on because somebody decided to do science for one thing instead of another. But the cost of doing a mission is more than just the cost of the equipment and the cost of the salary of the scientists. Years ago, I gave a talk at a beautiful university on the coastline of South Carolina in Charleston, South Carolina, College of Charleston. It was a lovely place. I gave this great talk on the moons of Jupiter. One of the students came up to me afterwards and said, "That was really great. I want to be a geologist." And I'm thinking, this is marvelous. Geology is a wonderful thing to study. The science is fascinating. You get to actually use chemistry and physics in the real world, not just, esoteric, theoretical, this is the way it ought to be, but this is the way it really is. Plus, if you do the right kind of geology, you get to go outdoors. And you get to go hiking in some of the most beautiful parts of the world. So I said, yeah, this is great. I really encourage you. And then he turned to me and he goes, "What do I tell my mom?" Your mom? I said, "I get that." South Carolina, what we call the Bible Belt, land of fundamentalists, Land of people whose idea of Christianity says that you must believe the Bible, which tells you that the world was made 6,000 years ago. The Bible doesn't actually say that, but somebody told them it said that, and they haven't gone back and checked. For him to become a geologist would mean that he would have a job that his mother would be ashamed to tell her family about, that he would have a hard time going home without everybody looking at him in shame. We have families, all of us. We have desires, all of us. We are a mixture of reason and heart, and the heart that has reason that reason does not know. We have to answer to those desires, both the ones in ourselves and the ones who really mean a lot to us, like our parents, like our family, like our community. There is this temptation to divide the world of science into faith and reason as if it was, Spock and Kirk. Actually, Spock and Kirk aren't even Spock and Kirk, because Spock was a very, very emotional rationalist, very suppressed. And Kirk was very, very clever in the way he managed to do the things he wanted to do. But beyond that, it's on the basis of both reason and gut feeling that we make all the big important decisions in our lives, where we're going to study, who we're going to marry, what jobs we're going to take, what city we're going to live in. I get asked about science and faith a lot. It was at one of those conversations that I finally had an insight as to where these people are coming from, why we do the science. In that conversation, oddly enough, was with Captain Kirk. There I am, in case you can't tell, that's no longer Leonard Nimoy. How I wound up talking to Captain Kirk is when William Shatner, the actor there, it's a long story. But when I finally described to him that I was a Jesuit brother and scientist, he was stunned. He goes, wait a minute. I can hear him, I can still hear, wait a minute. How is that possible? I don't understand. So we started talking, and I realized that the problem that he had is actually a problem that a lot of people have. And it was a problem that never occurred to me that people might have, because I don't have it. And I suspect the people in this room don't have it. He saw science as a big book of facts and religion as a different big book of facts. And what happens if the fact in one book doesn't match the fact in the other book? The point is, of course, that that's how we teach science and faith to 12-year-olds. You pass the course by getting the answer in the back of the book. But by the time you're at university, you realize the real science is the stuff that's not in the books yet. The real religion is not the stuff that's in the catechism, but the stuff where you have to use the worked out problems to figure out, now, how do I actually make these decisions in real life? But too many people stop studying science when they're 12 and stop studying religion when they're 12. But let me go a little bit deeper than that. Ptolemy had the system on one side to describe the motions of the planets in the sky against the stars. Kepler had a different system. Ptolemy was able to measure precisely and predict with a mathematical rigor where the planet was likely to be next by having a circle and then circles are orbiting around that circle and then circles within circles within circles. And any of you who have studied mathematics realize that this is basically a Fourier series. And if you have enough circles, you can trace any path perfectly. Go to YouTube and look up Homer Simpson Ptolemy. Somebody has worked out a Ptolemaic system that will draw a picture of Homer Simpson. No joke. That's the power of Fourier series. The Keplerian orbits are not perfect. They don't account for the fact that there are other planets perturbing on these planets. If Kepler had one more decimal point of precision, he would have despaired, because at that level, he would have found out the ellipses don't work. Thankfully, he didn't know that. So which system is better? Well, Ptolemy will get you the more precise answer, but that's not the science. Because the extra numbers don't actually tell you anything about what's going on, whereas the ellipses of Kepler confirm Newton's idea of a law of gravity. Science isn't getting the answer. Science is getting the insight and then coming up with a better question. And I don't think I have to mention here that faith is also not a bunch of rigid certainties. You may have heard the wonderful phrase from Anne Lamott. I just knocked this microphone, sorry about that. You may have heard that wonderful phrase from Anne Lamott: the opposite of faith is not doubt, the opposite of faith is certainty. And if you don't know that, look up Paul Tillich, who wrote an entire essay on the topic of the importance of doubt to faith. That's completely the opposite of what William Shatner thought faith was. He'd heard that phrase, blind faith, and he thought, oh, I have to go through life with my eyes closed, just trusting that God is going to make sure I don't fall off the cliff. No, that's not in Scripture at all. Remember what Moses says to the people after he gives them the tablets of the law. Do not forget the things your eyes have seen, or let them fade from your heart as long as you live. Teach them to your children, to their children after them. It's not close your eyes. It's rather teach what you have seen. Blind faith is not walking around with blindfolds, blinding yourself to the truth. It's proceeding after you've done everything you can to get as much data as you reasonably can and realizing that I don't have enough data and I have to make a decision anyway. Sometimes you gotta make a decision and you're never gonna have adequate data. The decisions about whether I'm going to be a scientist, these are decisions not only made on the basis of inadequate data, but they're made by stupid teenage kids, the people we were when we made that decision. The guy without the beard is me, as of 1974. I had even longer hair before then. How did I wind up being a planetary scientist? I actually had started out at Boston College. But my first best friend was going to MIT. I'd visit him on the weekends, and they had weekend movies, and they had pinball machines, and they had tunnels that would connect one building to another building. Those are the tunnels. Those are really cool to explore in the middle of the night. And sometimes you'll see through windows science going on. They also had the world's largest collection of science fiction stories. So out of the blue, I decided, yeah, I'll go there. I want to learn everything anyway. When I got there, when they actually accepted me as a student, I was ecstatically happy. I was happy like I never thought I could be. It was just, I was good at, sorry to the microphone again, I was good at the stuff they were having me learn, but it was also where my passion was. It turns out it wasn't the science fiction, it was the science. It wasn't the tunnels, it was the exploration. It wasn't, going to see weekend movies. It was exercising my imagination. And it was doing it as part of a community, a fellow community of nerds. Okay, yes, I felt like an imposter. Turns out everybody there thinks they're an imposter. But, for every Harry Potter fan who wants to be a magician, more of them, I think, would like to belong to a school where they've been sorted into people where they belong. More than the adventures of being in the Lord of the Rings, we all want to be part of a fellowship. Science is sharing stories about what we've learned And to share stories, you have to have a community. And without a community interested in hearing your story, you don't have anybody to tell it to. And not just stories about, where to go to school, or eventually people want to hear about your stories of the adventures in the lab and what you learned. Science is done as a part of a big community. And if you don't have the support of a community, you can't have science. Consider this. A bunch of mountains in India. You may have heard of the Himalayas. There's snow up there. There's a lot of people there. There's even skiing there. How many Winter Olympic medals have been won by Indians? The answer is 0. Not because they don't have snow, not because they don't have good athletes. What they don't have is moms who will take their daughters to the ice skating rink at 4 a.m, dads who will encourage their kids to be skiers, and a community where after you've done your Olympics, you can go back and teach the next generation. That whole, for whatever reason of their society, that whole structure just isn't there. If the society you live in doesn't think that doing science is part of a thing that's going to make a mother proud, you're not going to find very many kids who choose to do science. And you won't find anybody who can teach it to, or anybody who will teach you. In fact, there's something else going on. Ancient India, let's go back to, was way ahead of the world when it came to mathematics. What we call Arabic numerals are actually Indian numerals that the West got through Arabia. They had mathematics way in advance of anything in the West, but they did not have natural science. Why? Because in that culture, the physical world was a place of test and trial. For the ancient Chinese, the highest achievement was to be a person of culture and ethics. For the Manichaeans, here in Rome, the idea was that the physical universe was a source of temptation and evil, and we should rise ourselves above it. Chocolate was put on earth by the devil to tempt you into overweight and acne. No, says Christianity. No, say the people of the book. The universe was created by God deliberately and good, and chocolate is a foretaste of the goodness of heaven. It's almost a sacramental. For Christianity in particular, to believe that God so loved the world that he became a part of it, not loved good people, not loved ethical behavior, loved the world, puts a whole new spin on the relationship that we have with the physical world. And if nothing else, it means I can explain to the people of my culture why studying the physical world is a worthwhile, why Thomas Alberta could be, Albert the Great could be studying fossils and wondering about the physical world rather than being told, don't worry about that. That's not a proper thing for a person to study. Quite the contrary. It was so proper that we've made him a saint. These same questions affect the choices of individuals. Why does any individual decide to become a scientist? So I'll go back to my Peace Corps days. This is a film up here of a game called Hacky Sack. And when I was in the U.S. Peace Corps, this is the kind of thing we do in breaks between learning Swahili. Basically, you've got a little bean bag, and you throw it up in the air, and you try to kick it, and you kick it around until it drops in the ground, and then the next person picks it up. So we had one of our Peace Corps volunteers came from New York City, and her boyfriend shows up during Peace Corps training. This is before we went off to Africa. And he's watching us all playing hacky sack, and he goes, I don't get it. You're not trying to steal it? You're not trying to knock down the other guy? You're not keeping... How do you win this game? Well, science is a lot like hacky sack. It's a cooperative activity. You gain status by how much you pass off to the next guy, what you've added to the field, how much your work can help out the others in the field. You try to keep a lot of these ideas up in the air, keep them alive, pass them on to the next player, and there's never a moment where you say, I won, you lost. So, like the poor grad student in PhD comics here, what is your ambition? What makes you decide I've won? What counts as winning? Winning the Nobel Prize or getting a pepperoni pizza at the next colloquium? There are plenty of obvious criteria for winning the game. You win when you get the approval of others, when you get tenure, when you get grant money or prizes or fame or great students or your papers are cited. Is that why you're doing it? Are those ends in themselves? So, you've been working for 3 years and you've been a co-author on a paper called The Effect of Collective Molecular Reorientations on Brownian Motions of Colloids in Nemitic Liquid Crystals, which appeared in Science in 2013. And you are one of the et al. In the long list of et als in this paper. Is that why you spent the last 3 years doing the work? What are the personal motivations that make you enjoy being a scientist? Your curiosity, your pleasure in solving problems, in finding patterns. Maybe it's just, oh, little guy, he's really smart. He's a scientist. He went to MIT, and you like being patted on the head. Maybe you just, for reasons you can't explain, just love hanging out with these people or in this place. Okay, you're on a search committee, and you've got to choose who you're going to hire. Are you going to hire somebody who's coming in with grant money, prizes, and academic freedom, or are you hiring people who love solving problems? Would you sacrifice anything on one list to get something on the other list? Would you give up the approval of others to satisfy your curiosity, or vice versa? Would you give up the choice of tenure to do the kind of work you love to do, or vice versa? Would you give up academic freedom to be able to have a sandbox where you get to solve problems, even if it's problems that somebody else gave you, because they're the ones paying you? Would you decide to work in a field that's going to get you in the New York Times, or a field that has really cool patterns that only you notice? Would you give up grant money in order to get the approval of your friends, or vice versa? It's never that easy a decision. Because if you're not being paid to do the work, you can't do the work. And if you're not in a community of people who are interested in the work, then you're not doing science. Because, as we said, without that community, you've got nobody to share your stories with. Where is your heart, of course, then reflects where is your God? And what does that say about the kind of God you're worshiping? Internal motivations are essential. If you're not motivated to get up in the morning, you won't do the work, but it's not enough. Something has to be the ultimate criterion. And if you lose sight of why you're doing it, then the work becomes meaningless, and then you don't do it very well, and then you don't get another job, and you don't do it at all. So why do we do it? Whenever I've had those burnout moments in science, and I'm just like, why am I going to the lab? I find talking to kids is the greatest motivator. And they can be kids of not any age. I had 20 years ago the chance to teach physics for a semester at Fordham University. And I asked to teach second semester E&M because this was a class that had really opened my eyes to the joy of science. And I was teaching Maxwell's equations. These are Maxwell's equations on my t-shirt. And I came in and I said, at the beginning of the class, none of this makes sense to you. By the end of the class, you will know what all these symbols mean and you'll get the joke. So, the day had come when finally I had turned these into a differential form, and I was writing down the equations and a mu here and a d by dt here and a d by dx here for the electric field and the magnetic field, and I started gathering terms and saying if I put all the d by dt and substitute terms, and eventually I wind up with a second order differential equation of just E in time versus space, second order differential equation in just B, the magnetic field, in time versus space. Enough eyes glazing over, you have no idea what I'm talking about? I step back to give the reveal as to what this means. And before I can say a thing, there's a kid in the front row. You always notice the best students sit in the front row. I don't know which is the cause and which is the effect, but kid in the front row looks up and goes, "Oh my God, it's a wave." Yeah. A term where the change of change in time looks like the change in space is what we call a wave. If I'm standing in one space and over time the water goes up and then down and then up and then down, or I freeze in time and I walk through space and the water goes up and down and up and down in exactly the same way, that's a wave. And these equations tell you that the electric field and the magnetic field come as a wave. And when you realize that, suddenly all sorts of things burst into possibilities. But the first thing that happens is you say, and the more important thing is not it's a wave, it's the, oh my God. These are the oh my God moments. These are the moments of joy. These are the moments of looking at the universe the way it really is, but with new eyes, prepared to see things you hadn't noticed before, but mostly prepared to look at how incredibly beautiful it is. We do the science for the oh my God moments, which is to say, we do the science for the joy. The fact that there is a universe at all is fascinating and mysterious. Even more astonishing is that it's rational and reasonable and able to be understood by creatures inside that universe. Every bit of science that we can extract from these images depends on Maxwell's equations and the fact that, oh my God, it's a wave. The fact that it's a wave gives us radio and electric power transmission of alternating current and eventually special and general relativity. And it takes a few semesters of physics to be able to go from Maxwell to general relativity, but give me a couple of semesters, I'll get you there. And when you do, take my word for it, take my students' word for it. It's an oh my God moment. In my 40 years of research, I've had a few of those moments, nothing big enough to be in Science or Nature, but it's not the paper that I remember. It's that oh my God moment. Let me end with one last Peace Corps story. This was the view I saw every morning walking from my apartment in Boston across the Charles River to my office at MIT in that skyscraper. And I was 30 years old. I was a postdoc, fifth year of postdoc. Anybody in the field knows 5 years of postdoc says you couldn't get a job. Why am I doing this? Yeah, I'm at MIT and Harvard. Sounds good, but I couldn't get a job, a permanent job. Clearly, my life in science was over. So I decided to quit it all and join the U.S. Peace Corps. I'd go someplace adventurous, do something exciting. So here I am in Kenya, a whole lot skinnier than I am now. And the first thing they did was to say, we're going to put you in a high school in the middle of nowhere where there's no black in the blackboards, no windows in the windows. And yeah, right. And then they saw that I actually had a degree in the science. Well, we'll put you in like a good high school in the center of the city. Okay. Well, actually, we'll put you at the University of Nairobi, where you will be teaching graduate students astrophysics. The very same thing I was doing in Boston. There was a certain logic to it because the guys I were teaching all had jobs waiting at the Kenya Science Teachers College to teach the teachers to, okay. But that's not why they wanted to learn this stuff. Not why my kids at the Starehe High School were excited about spaceships and going into space. Because every weekend, I put together my little telescope and a handful of slides, and they actually had slide projectors that would run off car batteries. And I'd give little talks about what NASA had seen, and everybody in their village. I was there with 80 other volunteers. They all wanted me to come up and give a talk. And everybody in the village would go, look at the slides. Oh, what have they found? And they'd say, can we look through your telescope? And they'd look at the moons of Jupiter, and they go, wow. How many people here have ever seen the moons of Jupiter in a pair of binoculars or a small telescope? Binoculars will do it, easy enough. Anybody here ever seen the rings of Saturn in a small telescope? Have you ever seen the rings of Saturn in a small telescope and not gone, oh, wow. I've been looking at them for 73 years and I still go, oh, wow. Now, as it happens, I had a cat when I was in Kenya, a very clever cat, much better at being a cat than I ever could be. But my cat never wanted to look through the telescope. It's something that makes us uniquely human. To think about, we could go to the moon. In fact, we did go to the moon. And I don't just mean those guys in the picture. All of us went to the moon. The creation story of Genesis, 7 days. The cosmology is Babylonian cosmology. What's in Genesis that's important and new and different? Well, the single God, the God who deliberately creates, the God who creates logically, the God who says everything is good. All of that is important. But what is the goal of Genesis? In the Babylonian myth, the goal was to create the city of Babylon. What's the ultimate thing that is made in the story of Genesis? Not human beings, that's only the sixth day. It's the Sabbath. It's the weekend. God created us for the weekend, when we can kick back at least one day and contemplate the universe and go, oh, wow, oh, my God. Whether we do that with poetry or science or philosophy. Not stuff that's going to directly put food in your stomach, but we don't live by bread alone. I'd read that someplace. And to deny that to anyone else because they were born in the wrong place or the wrong time is to deny them their humanity. To help the poor, the goal isn't to make them rich. Rich people are the problem. The goal is to make them rich enough that they can have a weekend, that they can take time off to contemplate the universe and the one who made it. That's what makes us more than just well-fed cows. And so, every morning, I look forward to going down to the lab, dropping meteorites and liquid nitrogen. I mean, meteorites are cool. Liquid nitrogen is cool. And I do it merely for the joy. And eventually I can plot the data and I might get an oh my God moment, like, how come all the dots aren't on the line, but above the line? Something's going on here. It's that oh my God moment that leads us to do the science. All science needs it. There are some scientists who may say they don't believe in God, but they have to believe in oh my God. Science only happens because of that. Nothing would happen without it. Thank you very much.